Welcome. Tonight we're going to drift deep beneath the surface into a quiet cave where crystals grow slowly, patiently, and beautifully. Before we begin, a small invitation. If you're watching with the lights low and you want to take part in the story, leave a comment with one word. The mineral you think is most peaceful. Quartz, calcite, amethyst, fluorite, gypsum. Any answer is perfect. I love reading what you choose, and it helps shape what we explore next. Now settle your shoulders. Let your jaw unclench. Let your eyes rest. And imagine the cave. A stone doorway opens into darkness. The air is cool, still, and clean. Your footsteps soften as the ground becomes smooth and damp. Somewhere ahead, water is moving, so quietly you can barely hear it. And in that slow water is the secret of crystal growth. Because caves are not only empty spaces, they are laboratories of time. They begin with rock and with water. In many parts of the world, caves form inside limestone. Limestone is made mostly of calcite, a mineral built from calcium and carbonate. At the surface, rain falls through air that holds carbon dioxide. That carbon dioxide dissolves into the raindrops, forming a weak carbonic acid. It's gentle, so gentle that you would never feel it on your skin. But given enough time, it can transform mountains. That water sinks into the ground. It moves through soil, through roots, through tiny cracks. And as it travels, it reacts with limestone, dissolving microscopic grains of calcite and carrying them away in solution. This is one of the calmest forms of power on Earth. Not forceful, not sudden, just persistent. A crack widens, grain by grain. A seam becomes a passage. A passage becomes a chamber. And in the darkness, a cave is born. Now imagine that water continuing its journey, droplet by droplet, into the cave ceiling. A droplet forms. It holds dissolved calcium and carbonate picked up from the limestone above. It hangs for a moment, trembling slightly, then it falls. As it falls through the cave air, something changes. Some of the dissolved carbon dioxide escapes from the droplet back into the cave atmosphere. When carbon dioxide leaves, the water can no longer hold as much dissolved calcite, so the mineral begins to return to solid form. A tiny ring of calcite is left behind on the ceiling, almost invisible at first, but it is the beginning of a stalactite. This is one way crystals grow in caves, by a quiet exchange between water, air, and stone. If you're still awake, here's a gentle question for the comments. Have you ever stood inside a cave? Any cave at all? If yes, what did it feel like? Peaceful, eerie, magical, or something else? One word is enough. Now let's move deeper. The cave corridor opens into a larger chamber. The walls glitter faintly where your light touches them. Not every sparkle is a gemstone. Often it's calcite, clear or milky, arranged in tiny faces that reflect light like frozen water. But sometimes caves hold other minerals too. Gypsum can appear as delicate needles or silky fibers. Aragonite can branch into strange coral-like forms. Halite, rock salt, can crust the walls in dry caves. And in volcanic caves, you may find different stories altogether. Basalt textures, lava ropes, and minerals that precipitate from cooling gases and fluids. Tonight, though, we'll stay with the slow chemistry of water and time. Let's talk about the first step of a crystal: nucleation. A crystal does not begin as a perfect shape. It begins as a tiny cluster, a few molecules arranging themselves into a stable pattern. This is nucleation. It can happen on a rough surface, inside a tiny pore, or around a microscopic grain of dust. Water carries dissolved material. But dissolved doesn't mean gone. It means the ingredients are waiting, spread out, held in a delicate balance. When the conditions are right, when the water becomes supersaturated, the ingredients start to gather. Supersaturated means there is more dissolved mineral than the water wants to hold. It's like a crowd that suddenly needs to find seats. So the mineral finds a place to settle. A stable cluster forms. Then more molecules attach, and the crystal begins to grow. Crystal growth is not random. It follows structure. Each mineral has a pattern and internal architecture. Calcite has one arrangement. Quartz has another. Halite another. That internal pattern guides the outward shape, the faces, the angles, the symmetry. These are expressions of order. And this is one reason crystals feel calming to look at. They are natural evidence of structure emerging from chaos. A gentle reminder that patterns can form, even in darkness, even over long stretches of time. Picture a thin sheet of water sliding down the cave wall. Not dripping, flowing. It leaves behind a smooth coating called flowstone. Over time, flowstone can build ripples and terraces like frozen waterfalls. In places where droplets fall into a pool, the impact can release carbon dioxide and deposit calcite in concentric rims. These rims can grow into small dams called rimstone. Water spills over them softly, like a miniature landscape. Every cave is a map of motion. Not fast motion, but steady motion. Let's slow down even more. Imagine a single stalactite. At its tip, a droplet forms again and again. Each droplet leaves behind a small deposit. The stalactite lengthens downward. Beneath it, on the cave floor, the droplets land. They splash slightly and release carbon dioxide. And a stalagmite begins to rise up. Sometimes, over centuries, the two meet. A column forms, linking ceiling and floor. And if you ever want a sense of geological time, imagine this. A typical stalactite may grow only a fraction of a millimeter per year. Some grow faster, some slower. But in general, cave formations are not rushed. They grow while generations come and go. They grow while forests shift, while climates change, while rivers wander across valleys. And still, the cave continues. Now, not all crystals in caves are part of speleothems like stalactites and stalagmites. Some caves expose mineral veins, cracks in rock that once carried hot fluids. These fluids can be heated by geothermal gradients, by volcanic activity, or by deep circulation. They move through fractures, dissolving silica, metals, and other elements. When conditions change, temperature drops, pressure shifts, chemistry changes, the dissolved material precipitates. This is how quartz veins can form. And where there is quartz, there can be beautiful variety. Pure quartz can be clear. With tiny amounts of iron and natural radiation over time, quartz can become amethyst, violet and calm. With different impurities, quartz can appear smoky, rose, or milky. If you'd like, pause for a moment and choose a color in your mind. Clear, white, violet, smoky gray, pale pink. Let that color fill the cave softly, like a gentle glow. And if you want to join in, comment your color, just the color. No explanation needed. Now let's walk toward a geode. A geode begins as a hollow space. Often it forms in volcanic rocks where gas bubbles left cavities as lava cooled. Or it can form in sedimentary rocks where nodules develop. The key is the hollow. Mineral-rich water enters that hollow through tiny pores and cracks. It deposits layers on the inside walls. Sometimes it starts with chalcedony, a microcrystalline form of quartz forming a smooth lining. Then, as conditions change, larger quartz crystals can grow inward, pointing toward the center. This is one of the most satisfying shapes in geology. A hidden chamber filled with points of light. In your mind, imagine holding a geode. It is plain and rough on the outside. Then it opens, and inside is a constellation. Crystals grow like this when there is space to grow. They need room. They need steady supply of dissolved material. They need stable conditions long enough for their faces to form. If conditions change too quickly, crystals may stay tiny. If the water dries too fast, growth can stop. If the chemistry shifts, a different mineral may begin to form on top of the first. So a cave can record changes in its layers, like pages. Now let's return to our cave chamber. There's a quiet pool in the center. The surface is dark and still. A single drip lands every so often, sending rings across the water. This is a good moment to breathe slowly. In and out. In and. The cave does not demand anything from you. It does not hurry you. It does not judge. It simply exists. Now, a gentle fact: cave crystals are often shaped by the balance between growth and dissolution. Even while a stalactite grows, the water can also dissolve parts of it. If the cave becomes more acidic, dissolution increases. If the cave air becomes drier, evaporation increases. If airflow changes, carbon dioxide levels shift. So the final form is not just growth. It's the result of many small influences. This is why some formations look smooth and rounded, while others look sharp and spiky. It depends on how quickly mineral arrives, how quickly it leaves, and how stable the conditions remain. In some caves, you can find cave popcorn, small knobby clusters of calcite or aragonite. They form when water seeps through pores and evaporates quickly. In other caves, you can find thin, translucent curtains of calcite, draperies, formed as water flows along slanted ceilings, leaving behind rippled sheets. And in rare places, you can find formations that look almost impossible. Stalactites, thin, twisting tubes that seem to grow sideways or upward. Their shapes can be guided by capillary forces, by airflow, by tiny variations in deposition. Small physics acting on small amounts of water, repeating for a long time. It's a reminder that nature can sculpt with whispers. Now, if you're still awake, here's another comment prompt, soft and optional. If you could visit one underground place, would you choose a crystal cave, an ice cave, a lava tube, or a deep ocean trench? Write just one: crystal, ice, lava, or ocean. Now we'll continue. Imagine we reach a section of the cave where the walls are lined with crystals, maybe calcite rhombs, maybe quartz points. Each face reflects a sliver of light, but most of the cave remains dim. This is how caves teach us to appreciate subtlety. Let's talk gently about why crystals have shapes. At the molecular level, atoms bond in repeating patterns. Those patterns can be cubic, hexagonal, trigonal, orthorhombic, many systems. The pattern determines which directions are easiest to grow. Growth is like stacking blocks. Some faces are stable and grow slowly. Other faces grow quickly and disappear. So a crystal's final shape is a record of its growth rates. Quartz often grows in hexagonal prisms with pointed terminations. Calcite can form rhombs, scalenohedrons, and more. Halite often forms cubes. Now imagine a quartz point. Its sides are smooth but not perfectly. On the surface are tiny growth lines, delicate steps where layers stacked one after another. Each line is a moment. If you want to feel time differently, imagine counting those layers. Not as years, not as centuries, but as quiet additions, as slow arrivals. Now we'll drift into a longer, calm section. More atmosphere, less explanation. We walk through the crystal cave at a relaxed pace. Our light moves gently across the floor. The air smells faintly mineral, like wet stone. Water beads on the walls. Somewhere, in a crack high above, a droplet gathers. It waits. It swells. And it falls. The sound is soft. Another droplet falls. And another. You can let those sounds become a metronome, not for thinking, just for drifting. In the darkness, crystals keep doing what they do, assembling, aligning, growing. No effort, no struggle, just physics, chemistry, and time. Now, let's return to the idea of mineral-laden water. Water is an excellent solvent. It can carry ions, charged atoms, through tiny spaces in rock. It can move silica, calcium, magnesium, iron, and more. But the cave is not isolated. It is connected to the surface above. If the climate becomes wetter, more water enters the cave, If the climate becomes drier, less water enters. If vegetation changes, carbon dioxide levels in soil can change, affecting acidity. So the cave becomes a silent archive of the world outside. Some cave formations can even be studied to understand past climates, because layers can reflect changes in rainfall and chemistry. But tonight, we won't analyze. We'll simply appreciate that the cave remembers. Now imagine moving deeper to a chamber where crystals are larger. This chamber feels ancient. The floor is uneven with deposits. Some formations are broken, perhaps by past floods, or natural shifts, or old collapses. The cave has had many phases. It has been wet, dry, wet again. It has been still, then active, then still. And through it all, minerals have come and gone, leaving shapes behind. A crystal is not only a thing, it is a process captured in form. Now, a gentle reminder that helps many people relax. You don't need to hold on to every detail. You can let the words pass like water. If you remember only the feeling of the cave, that is enough. In and out. Now let's explore one mineral in more detail. Calcite. Calcite is common in caves because limestone is common, and because the chemistry is favorable. Calcite is calcium carbonate. It dissolves in slightly acidic water and precipitates when carbon dioxide leaves the solution. Calcite can be clear like glass or white like snow. It can sparkle with tiny faces. It can form large crystals in some caves, especially where water chemistry stays stable. Some calcite fluoresces under ultraviolet light. But in our calm cave, the light is soft and natural. Now imagine a single calcite crystal face. It is flat. It reflects your light cleanly. It seems almost too perfect to be real. But it is real. Now quartz. Quartz is silicon dioxide. It often forms in different settings than calcite, but it can appear in caves, especially where silica-rich fluids have moved through fractures, or where geodes are present. Quartz is hard. It resists weathering. It holds its shape. This is part of why quartz crystals can look so crisp. Now, a soft engagement question. If you've ever found a rock you loved, any rock, what was it? It can be a pebble from a beach, a stone from a mountain path, a piece of glassy obsidian, anything. If you feel like sharing, comment what it was and where you found it. Short is fine. Now we'll drift again. The cave extends into a hallway that narrows. On one side, the wall is covered in tiny crystals, like sugar on stone. On the other side, smooth flowstone curves like frozen honey. We walk slowly. Our footsteps are quiet. We pass a formation shaped like a curtain, rippled and thin. Water once flowed here in sheets. Each sheet left a layer. Layer by layer, the curtain grew. We pass small columns, miniature towers. We pass shallow pools. We pass a shelf of rock where crystals cluster like stars. We pause. We listen. Somewhere, a faint drip. And beneath that sound, a deeper silence, a kind of silence you can feel. Now let's talk about impurities, because impurities create color. Pure minerals can be clear or white, but small amounts of other elements can tint them. Iron can create reds, yellows, browns. Manganese can create pinks. Chromium can create greens. Trace elements can shift tones subtly, making each crystal slightly unique. Even the same mineral can look different depending on its environment. And that is a comforting thought. Structure and uniqueness together. Now imagine a cluster of crystals with a faint blue tint. Maybe it's a trick of light. Maybe it's a tiny impurity. Either way, it's calm. If you want to, comment one more thing. Do you prefer crystals that are clear or crystals that are colorful? Just clear or colorful? Now we'll slow further into a lull designed for sleep. We return to the cave pool. The air is cool on your skin. Your breath is warm. The cave does not change quickly. A droplet falls. A circle spreads. Another droplet falls. Another circle spreads. You can imagine the cave as a clock that does not use seconds. It uses drips. It uses layers. It uses quiet repetition. Each drip is small, but each drip matters. Now, a final science whisper before we drift. Crystal growth is influenced by temperature. Warmer water can hold different amounts of dissolved minerals than cooler water. Pressure matters too, especially deep underground. So crystals can form in different shapes depending on depth and conditions. In caves closer to the surface, the main influence is often carbon dioxide exchange and evaporation. Deeper systems can involve hydrothermal fluids, but the feeling is similar. Minerals moving, then settling. Now let's imagine the camera drifting through the cave. Slow, steady, gentle. We glide past a wall of quartz points. We glide past a calcite column. We glide past a smooth basin filled with still water. The cave's colors are muted. Charcoal rock, pale mineral, cool blues in shadow, soft whites where crystals catch the light. Your mind can follow the motion without effort. If thoughts arrive, let them pass. If you lose track of the narration, that's perfect. Now we enter a chamber where the ceiling rises high overhead. From the ceiling hang thin stalactites, like stone icicles. Some are needle thin, some are thick and layered. Below, stalagmites rise like quiet hills. Between them are gaps filled with darkness. In that darkness, the cave breathes. And somewhere, very slowly, a crystal face expands by a microscopic fraction, an addition so small it feels imaginary. But it is happening. Now I'll guide you through a gentle cycle. This cycle repeats in feeling, not in exact words. We will visit water, stone, air, then crystals, time, quiet, again and again. Let's begin. Water moves through rock. It picks up minerals. It carries them silently. Water enters the cave. It meets the air. It changes. A mineral leaves the water. It settles onto stone. A crystal begins. A crystal grows. A layer forms. Another layer forms. The cave remains. Time passes. Water returns. Stone remembers. Air holds the silence. And the crystal grows again. Now again, even softer. Water moves. Stone waits. Air holds. Minerals drift, patterns align. Faces form. Time stretches. And the cave continues. Now again, a drip, a deposit, a pause, a drip, a deposit, a pause. This is enough. This is calm. Now, as we continue, you may hear occasional invitations to comment. Only take them if you want. If you're already drifting, let them fade. Now we'll explore a few cave scenes, like calm postcards. Scene 1, the crystal shelf. A ledge of rock curves out from the wall. On it, hundreds of tiny crystals sparkle like frost. They are not loud, they are not bright. They simply catch the light when it touches them. Scene 2, the flowstone cascade. A wall looks like frozen water, smooth and layered. It formed as thin films of mineral-rich water ran down and evaporated, leaving behind calcite and a soft glaze. Scene 3, the rimstone pools. A series of shallow steps hold water in quiet basins. Each step is a mineral dam. Water spills gently over the lip, whispering. Scene 4, the geode hollow. A round cavity opens in the rock like a secret. Inside, quartz points reach inward. The center is empty, a pocket of dark air that makes the crystals shine. Scene 5, the stalactite garden. Thin mineral tubes twist in unexpected directions. They look like tiny branches, like mineral vines. They grew slowly, guided by capillary action and subtle airflow. Now breathe. In and out. In Impamas two relaxations. They look like tiny branches, like mineral vines. They grew slowly, guided by capillary action and subtle airflow. Now breathe. In. Meet Whelms. If you're still awake and you want to support the channel, here's a simple way. Comment the scene you liked most. Shelf, cascade, pools, geode, or garden. Just one word. We continue. Nothing changes quickly down here. No alarms, no urgency, only water, stone, air, and time. If you're just joining, welcome. This is calm geology, made for rest, for focus, or for sleep. And if you'd like to quietly support the channel, you can leave a simple comment. Still here, or just a single dot. I see them, and they help more than you might think. Now, let's drift deeper. Chapter. The cave as a slow machine. A cave is a slow machine. Not mechanical in the human sense with gears and levers, but mechanical in the Earth's sense. A system that repeats the same gentle actions for a long time. Water enters. Water changes. Minerals move. Minerals settle. The cave is built by removal and decorated by return. First, water dissolves rock. Then later, minerals come back out of the water. They return as crystals. They return as layers. They return as shapes. A cave is subtraction, followed by sculpture. Now picture a long tunnel. Its walls are rounded. Its ceiling is smooth. This shape is not an accident. Water prefers to move along cracks. And once a crack widens, more water can pass through. More water means more dissolution. More dissolution means a wider passage. It's a feedback loop, but a gentle one. Like a path in a forest. Walked often, made clearer. And once the cave opens, air enters. Air changes the chemistry. Air changes the rhythm. Air makes crystal growth possible. Now, breathe slowly. In and out. Chapter Supersaturation, the moment of return. In the last section, we spoke about supersaturation. Let's revisit it slowly. Water can carry dissolved minerals, but water has limits. Those limits depend on temperature, pressure, and chemistry. When conditions shift, the water becomes supersaturated. That means the ingredients are ready to leave the solution. They want to return to solid form, and when they return in patterns. This is the calm magic of crystals, matter organizing itself. You can imagine it like this: a crowded room, everyone moving. Then a slow, steady music begins. And the room starts to arrange itself, step by step, into a dance. Not forced, not rushed, just guided. Chapter Stalactites, one drop at a time. Now we stand beneath a ceiling where a stalactite hangs. It is not loud, it is not dramatic, it is patient. At its tip, a droplet forms. It gathers dissolved calcite. It hesitates, then it falls. As it falls, carbon dioxide escapes, and a tiny bit of calcite is left behind. Then it happens again. Drip, deposit, pause. Drip, deposit, pause it. If you're listening for sleep, let that rhythm become a lullaby. Drip. Now imagine the matching stalagmite below. The droplet lands. The splash helps carbon dioxide leave. Calcite settles. The stalagmite rises. Ceiling grows downward. Floor grows upward. And sometimes, after a very long time, they meet. A column. A slow handshake between roof and ground. Chapter Cave Curtains and Frozen Waterfalls. We move along a wall that looks like frozen honey. This is flowstone. It forms when water does not drip but flows. A thin film spreads across the rock. As it moves, it loses carbon dioxide. It evaporates slightly. It deposits calcite. Layer by layer, the wall becomes glossy, like stone that remembers water. In some places, the flowstone forms curtains, draperies of calcite. The curtain begins where water follows a slanted ceiling. It leaves behind a line of mineral. Over time, the line becomes a thin sheet, and the sheet ripples because the water ripples. The result is quiet and beautiful. If you've ever seen a cave curtain, you know it looks like stone fabric, a mineral waterfall, frozen mid-motion. If you're awake and you want to comment, choose one word: velvet or glass. Velvet for curtains, glass for flowstone. Now deeper. Popcorn needles in strange forms. Not all cave crystals are smooth. Some are knobby clusters called cave popcorn. They form when water seeps through tiny pores and evaporates quickly. The mineral arrives in small bursts, leaving rounded shapes. Some are needle-like. Gypsum can grow as slender blades. Aragonite can grow as delicate sprays. Some form stalactites, twisting mineral tubes that appear to defy gravity. Their growth can be guided by capillary action, air currents, and tiny imbalances. A little more mineral deposited on one side than the other. A little airflow, a little evaporation, and the shape curls. It's not that physics breaks, it's that physics gets subtle. The cave's breath. Caves breathe. Air moves in and out of openings. Temperature differences drive circulation. Seasonal changes can reverse airflow. This matters because carbon dioxide matters. If carbon dioxide is high in the cave air, calcite may dissolve more easily. If carbon dioxide is low, calcite may precipitate more easily. So cave formations are shaped by breath, by ventilation, by stillness. Even silence has chemistry. Now let's slow again. In and out. Quartz veins and deep fluids. Not all crystals in caves are made by dripping water. Some are older, born from deeper fluids. Quartz veins form in fractures. Hot water, hydrothermal fluid moves through cracks. It dissolves silica, it transports it, then the conditions shift. The fluid cools, pressure changes, chemistry changes. Silica precipitates, quartz grows. Quartz can grow clear and glassy, or smoky, or milky. And with trace impurities and time, quartz can become amethyst. Violet, calm, and deep. Now imagine a vein of quartz cutting through dark rock. A pale line through stone. A signature of fluid motion from long ago. Comment prompt. Mineral vote. If you want to steer future videos, comment your favorite. Quartz, quartz, calcite, gypsum, amethyst, fluorite. One word is enough. Now we'll drift into a longer calm sections. Crystal faces and growth rates. Why does a crystal have faces? Because growth is not equal in all directions. At the microscopic level, molecules attach more easily in some directions. Those directions grow faster. Fast-growing faces disappear. Slow-growing faces remain. They become the visible surfaces. So a crystal's shape is a map of its growth speeds. A quartz point is a record of hexagonal order. A salt cube is a record of cubic order. And if you look closely at a crystal face, you might see fine lines, growth steps, tiny terraces where layers stacked. Each line is a moment, not a human moment, a mineral moment. Evaporation crystals in dry chambers. Some caves are dry. In dry caves, evaporation becomes powerful. When water reaches a dry chamber, it can evaporate quickly. As it evaporates, dissolved minerals are left behind. This can form crusts and sparkling coatings. In salty environments, halite can appear. In gypsum-rich settings, delicate crystals can bloom. These crystals can be fragile. They can dissolve again if humidity rises. So the cave becomes seasonal, a slow breathing cycle of crystal appearance and disappearance. If you're awake, comment your preference. Night cave for wet and dripping. Dry cave for crystalline crusts and still air. Now, deeper. Rimstone pools, the smallest dams. We arrive at rimstone pools. They look like tiny terraces, little steps holding water. Rimstone forms when calcite precipitates at the pool edges. Water spills over. Mineral deposits build the rim. The rim grows. Over time, a staircase of pools forms, one of the gentlest architectures in nature. A slow builder making miniature dams. Water is calm here. If you are trying to sleep, imagine the surface of the pools. Dark, smooth, reflective. A drip lands. A ring spreads. Then stillness. Cave pearls, the rolling stones. Some caves create pearls. Cave pearls form when tiny grains roll in shallow pools. Water splashes and deposits calcite in thin layers. As the grain rolls, the layers coat evenly. Like a pearl in an oyster, but mineral. Cave pearls are rare. They need just the right environment. Shallow pool, gentle movement, steady mineral supply. They are small, quiet treasures. Now imagine one in your hand. Not shiny like jewelry, but softly smooth. A stone that learned patience. Colors, light, and calm perception. Many crystals are clear or white, but color comes from impurities. A trace of iron, a trace of manganese, a trace of copper. Tiny changes, big effects. Color is chemistry. But in caves, color can also be light. The way your lamp reflects. The way shadow softens edges. If you want a calming exercise, choose one cave color. Cool blue, pale white, smoky gray, violet, soft amber. Hold it gently in your mind. If you want to comment, write only your color. The cave is an archive of outside worlds. Caves connect to the surface. Rainfall changes the drip rate. Vegetation changes soil carbon dioxide. Temperature changes airflow. So the cave records the outside world. Layers can reflect wetter years and drier years. Some scientists study cave deposits to learn about past climates. But tonight, we won't analyze data. Tonight, we simply appreciate that the cave remembers. And we let that memory be calm. Quiet repetition. We move again through the cave. Slow camera glide. Past a crystal shelf. Past a flowstone cascade. Past rimstone pools. Drip, pause. Drip. Pause. If thoughts arrive, let them float away like mist. If you lose track of the words, that is perfect. The cave does not need your attention. It accepts your presence. Drip. Pause. The cave returns to silence. We return to the pool. Drip. Pause. The water is cool. The rock is steady. Foliage is it, you morphers working. I feel your body getting heavier. Your thoughts getting quieter. If you fall asleep now, the cave will continue without you. Crystals will keep growing. And that is comforting. A gentle recap, like waves. Let's recap softly. Caves form when water dissolves rock. Crystals form when minerals return from water to stone. Stalactites grow from ceilings. Stalagmites grow from floors. Flowstone forms from sheets of water. Geodes form in hollows. Quartz veins form in fractures. All of it is water and time. All of it is slow. Now, we continue the calm journey. Choose the next journey. If you want to help choose the next calm science video, comment one option. Glaciers, volcanoes, deep ocean, deserts, space. One word. Now we drift deeper once more. The Crystal Cave Sleep Loop extended. From here, the narration will move in a gentle loop, revisiting the same themes with slight variations, so you can relax without needing to follow. We begin. We walk through the drip hall. Stalactites above. Stalagmites below. A steady rhythm. Drip. Pause. Water moves through limestone. It carries calcium and carbonate. In the cave air, carbon dioxide leaves. Calcite returns. Drip. Pause. We pass a curtain gallery. Stone fabric ripples. A soft shine. Flowing water leaves layers. Layer after layer. Drip. We stand by rimstone pools. Still basins. Quiet reflections. A ring spreads on the surface. Then stillness. Drip. Pause. We enter the geode chamber. A hollow lined with quartz points. A quiet constellation. Minerals arrive. Faces form. Space remains empty. Drip. Pause. We move past crystal shelves. Tiny sparkles. Soft light. And again. Drip. Pause. If you're awake, you can comment. Loop. Just that word. It tells me you made it into the deep part of the video. Now we continue. And now, we've reached the end of our journey. Thank you for spending this quiet time in the crystal cave with me. If you fell asleep, I hope your rest was deep and gentle. If you stayed awake, I hope you felt a little calmer than before. Before we go, I'd love to hear from you. Which part did you enjoy most? Drips, flowstone, geodes, or quartz veins? Leave one word in the comments. I read them all. If this calm science style helps you, you can support the channel by liking the video, subscribing, and sharing it with someone who could use a peaceful night. Wherever you are in the world, may your mind be quiet, may your breath be steady, and may your night be soft. Good night.